few videos on the intermediate value theorem. I want to motivate it with a very explicit algebraic example or a solving equation kind of prompt. There's a lot of ways to think about the intermediate value theorem. But I kind of want to start with something that's a tiny bit more interesting and complicated than the basic case that you see in the theorem, because I want to emphasize that it's not just about repeating the same theorem over and over again. So suppose you had this task: solve a natural logarithm of x equals x e to the minus x. It looks like an algebra problem, and it looks like we would maybe take logs again. Well, but that means log of a log, or we'd do something, divide or subtract or something. Turns out you can't solve this algebraically. There's no algebra you could possibly invent that would isolate the x. So that's unfortunate. Well, you're not going to get some sort of exact, pretty solution to it, but you could try to then search for some sort of numerical approximate solution. And a very reasonable thing is to say, let's call the left-hand side, let's say f of x, and we're asking, where is that equal to g of x? We'll call the right-hand side g of x. And you could graph f and g and see where they intersect. Hopefully you've done that at some point where you've been in a situation where you wanted to solve where two quantities are equal, two functions are equal, and you just couldn't do it algebraically. So let's see. Let's actually graph those guys. I have a little table here. Okay, some decimals. So ln x is pretty straightforward. It's a good thing to be familiar with, certainly. Starts out way down here has a vertical asymptote way down here, and then comes up through 1, 0, and then at 2 it's about a little over 2/3, 0.69, and then at 3 it's a little bit over 1, so something like that. So it's increasing. X e to the x, on the other hand, is a tiny bit more interesting. It's a great function because of the x. When x is 0, it's going to give you 0. When x is 1, it's just going to give you 1 over e, which turns out to be about 0.37, about 1/3-ish. Oh, I guess I was using orange for that. Okay. And then it actually starts going down again because the e to the minus x starts decaying. So it's 0.27, about a quarter, then about a sixth-ish, seventh, something like that. So it actually turns out to be up, and it turns out the max is right there. That we'll discover that, how to prove that with calculus very nicely soon. And voila, it looks like there is going to be an intersection. Okay. Then this is where the theory comes in. I didn't plot this point. I don't know what it is exactly. I don't have anything where these two numbers are equal exactly. Can I really assert confidently that there really is a point of intersection here where some x, where f of x equals g of x, that, in other words, this solves this equation? It's our intuition that they should cross. But what is our intuition based on? It's based on the intuition that these are continuous functions, that I have this continuous curve here and I cross it, and there must be somewhere, some place that I cross it. And the intermediate value theorem is all about making that more precise. So it's often good to first think about, how could that ever fail? How could that possibly be wrong? Well, what if we had, let's bring in another color. What if the graph of x e to the minus x was actually something like this, where it started out like this, went up, and then suddenly jumped across the blue line of ln x? Then, just because it started out on one side and ended up on the other, doesn't mean there has to be any particular point where they actually are touching, where they intersect, and there would be no solution to this. But of course, we can see that the difference between this orange curve, x e to the minus x, and this fake red curve is exactly that I had to make it discontinuous. I had to jump over it. I had to jump over the blue curve in order to not cross. So what I claim is the key, the simplest thing to concentrate on, to really focus and get a very clean, easy to state, easy to use theorem, is the fact that there's one point, x equals 1, where orange was above blue. That was a very straightforward calculation. Then, later on, at x equals 2, as it happens, blue is above orange. They have switched places, so they had to cross. But again, very much counting on the fact that these are both continuous functions. There's no gaps in either of them. And that's going to be a nice, slightly more elaborate version of the basic intermediate value theorem. So let's even strip it down a little bit more, though. A very common technique when you're trying to set two things equal, you've been doing this since the first days of algebra, is to say, well, what if I can express it as ln x minus x e to the minus x. Can that ever be equal to 0? And can I solve that equal to 0? Just put everything on one side of the equation. Very, very standard. Or in slightly more generality, take those two different functions, create a new function that, and then all we have to do is say, is it equal to 0? So that's going to be a slightly simpler version, and that's how you usually see the theorem phrased in terms of one function, and can I assert that it has to be equal to some constant value? You could even specialize to 0, but often that's left to be some unknown constant value. So the graph of that, I'm going to leave the details of that to the next video, but the situation there, so let's even erase this. We'll come back to this exact problem. Don't worry. We'll say more about it. Okay, so the new simpler problem, though, is when can I assert, let's say, I believe n is what our book uses. When can I assert that I have some function so given some function, when can I, and some value, when can I assert that I must be able to solve f of x equals n? Or graphically, when can I claim that it must cross a certain horizontal line? And we're just going to end up saying in precise terms that that's going to happen if I start on one side and then I end up on the other, as long as I know that f is a continuous function. So let's start the next video with that precise statement.